This is Physics 2120, Lecture 8, and today we're going to talk about dielectrics and dipoles. A dielectric is a non-conducting material that when placed between the plates of a capacitor increases the capacitance. Dielectrics include things like rubber, plastic, paper, and when we have a dielectric, when we place it in a capacitor, it's going to increase the capacitance. For a parallel plate capacitor, we see that the capacitance is kappa C naught, where C naught is the capacitance without any dielectrics in it. So, and kappa is the dielectric constant. So the capacitance is multiplied by this factor kappa when it completely fills the region between the plates. In theory, we could make D very small to create a very large capacitance. And in practice, though, there's a limit to D. D is the distance limited by the electric discharge that could occur through the dielectric medium separating the plates. In other words, if I get plates too close together, I could get charge jumping from one plate to another. For a given distance, the maximum voltage that can be applied to a capacitor without causing this discharge depends on the dielectric strength of the material. So dielectrics provides certain advantages. Number one, they increase the capacitance. Number two, they increase the maximum operating voltage. And number three, they offer a possible mechanical support between the plates. Allows you to push the plates very close together without touching. Decreases D and increases then the capacitance. So table 26.1 here shows us some dielectric constants and strengths of various materials, dielectric strengths of various materials at room temperature. So for example, bakelite here has a dielectric constant of 4.9. So if I had a parallel plate capacitor and I put bakelite in between it, it would increase the capacitance almost 5 times. Or strontium titanate, 233. I can increase the capacitance 233 times by putting strontium titanate in between it. Even water has a large dielectric constant. Then over here, the dielectric strength tells us how much voltage can be on something before you get breakdown, you get sparks or electricity jumping charge from one to the other. For example, in air, dry air, it's 3. That means 3 times 10 to the 6 volts per meter. 3 million volts are required to get a charge to jump 1 meter in dry air. Now briefly, let's look at different types of capacitors. And the first you might see is a tubular capacitor, where the plates are these metal pieces of metal foil. And I take the metal foil and I put some paper down in between them. When I roll this up, essentially what I've done is I've created a very large parallel plate capacitor. But instead of the plates being in a plane, these plates are rolled up. And so that the area of this parallel plate capacitor would be the height times the length of this roll. And if it's very thin metal, you could roll up a very large amount of this metal. Oil capacitors are common for high voltage capacitors. And I'll have a sealed container here, and inside the sealed container will be filled with oil, which is a dielectric. And then I'll have one side connected to a series of plates, and another side connected to some other plates. And then I get the capacitance between those plates. Electrolytic capacitors, or if you've ever seen any circuit boards, are the little round disc capacitors you see on the circuit. And they're used to store large amounts of charge, but very low voltages. The electrolyte is a solution that conducts electricity by virtue of motion of ions contained in a solution. And finally, a variable capacitor. The picture here shows a variable capacitor that just is two interwoven sets of metallic plates. One plate is fixed and the other rotates and moves. And then by rotating one set of plates into the other, I can change the contact area, or not the contact area, the area of the plates that are opposite each other. And those capacitors typically can vary between maybe 10 and 500 picofarads. They're used a lot in radio circuits for tuning. So let's look at a problem. A parallel plate capacitor of dimensions 2 centimeters by 3 centimeters is separated by 1 millimeter thickness of paper. What's the capacitance, and what's the maximum charge that can be stored on the capacitor? And if the voltage across the capacitor is held at 100 volts, how much work must be done to remove the paper? So first, what's the capacitance? Well, it's a parallel plate capacitor. The capacitance is going to be kappa C naught, where C naught is epsilon naught A over D. It's the standard equation for the capacitance of a parallel plate capacitor. We look up the capacitance for paper. Kappa is 3.7. We plug in our values and we get 20 times 10 to the minus 12 farads, or 20 picofarads. What's the maximum charge that can be stored on the capacitor? Well, the maximum voltage that can be on the capacitor is this Emax. This is that breakdown field that we talked about on that table 26. So it's a parallel plate capacitor. Electric field is constant in there, so we can use V equals ED. We look up the maximum electric field for papers, 16 times 10 to the 6 volts per meter. Multiply it by the distance, and we get 16,000 volts. Then we know that the charge is capacitance times voltage. We plug that in, and we get the maximum charge it can handle is 0.32 microcoulombs. And finally, if the voltage across the capacitor is held at 100 volts, how much work must be done to remove the paper? Well, first, what is the energy stored in the capacitor with the paper in there? Well, it's 1/2 CV squared. We said the capacitance was 20 picofarads. The voltage we said is 100 volts, and so we get 10 to the minus 7 joules. Now, when the paper is removed, the capacitance is just going backwards. 20 picofarads divided by that 3.7, so that's 5.4 picofarads. The energy stored in the final configuration is 1/2 that capacitance V squared. We plug that in, we get 2.7 times 10 to the minus 8 joules. So the work required to remove the paper is just going to be the final energy minus the initial energy. So the amount of work it requires is 7.3 microjoules. Now the next thing I want to talk about is an electric dipole. We mentioned electric dipole before. Remember, it is two charges of equal magnitude and opposite signs. And the separation distance between them we'll say is 2a. The electric dipole moment is a vector quantity whose strength depends on the amount of charge and on the separation of the charge. And its direction is along the line joining the negative charge to the positive charge. The magnitude of the electric dipole is the distance between the charges times the charge, so 2aq here. Now, let's assume that this dipole is placed in some external electric field. This is external to the dipole. This is not the field created by the dipole. And let's assume that the dipole makes an angle theta with the field. So each charge on this dipole has a force, which is E times the charge acting on it. Now, if these things are connected somehow, the net force on this dipole is 0. The force on the positive charge is in the direction of the electric field, and on the negative charge is opposite. Equal charge, same field, means the net force on it is 0. However, if I imagine some center of this dipole, it's going to have a torque that's going to want to cause this dipole to rotate. The magnitude of this torque is force times the distance between the torque times the sine of the angle. So in this case, if we multiply it out, it's going to be the dipole moment times the electric field times the sine of the angle between the dipole and the electric field. Of course, we can also express torque as the cross product of the moment in the field. So torque is P cross E. And the potential energy can be expressed as a function of the orientation of the dipole with the field. So the energy is the integral of torque d theta. Just like energy is the integral of f dx, we can consider it torque d theta, and the torque is Pe sine theta d theta, integrated from some initial to some final position. Of course, Pe are constants, they come out. If we integrate sine, we get minus cosine. And so the potential energy between the final and initial is Pe times cosine theta initial minus cosine theta final. So in other words, the energy is negative Pe times the cosine of the angle that this dipole is sitting in the field. Or we can use our dot product. It's minus P dot E. That brings us to different molecules. Molecules can be polarized when a separation exists between the average position of the negative charges and the average position of the positive charges. Now, polar molecules are molecules where this condition is always present. But even without a permanent polarization, molecules can be polarized. Those type of molecules are called non-polar molecules. A water molecule is an example of a polar molecule. The center of the negative charge is near the center of the oxygen atom. And X is the position of the positive charge distribution. So that means that between these two places there is a dipole moment. The dipole moment would point from the negative charge down towards the positive charge. The average positions of the positive and negative charges act as point charges, and therefore polar molecules can be modeled as electric dipoles. Now, besides a polarization that is permanent, we can also induce a polarization. So, for example, in figure A, we see a symmetric molecule that has no permanent polarization. CO2 has a similar form, a linear chain of atoms. However, if I place this molecule in an external field, the positive charges are going to feel a force one way, and the negative charges in the other way. And I get an induced polarization, and this induced polarization is the effect that predominates in most materials used as dielectrics and capacitors. So, if I look at an atomic view of what a dielectric is, we have these molecules that make up the dielectric, and we model them as dipoles, and they might be in all sorts of different orientations. They're completely randomly oriented in the absence of an electric field. Now, when I turn on an electric field, something happens. There's no net force on these molecules, so they don't move. However, there is a torque on all those molecules, and those molecules try to turn to line up with this electric field. Now notice when they do line up that all the positive charges tend to be on one side and the negative charges tend to be on the other side. That means that along the surface of this dielectric there appears to be a negative surface charge. On the surface of this there appears to be a positive surface charge. The degree to this alignment depends on things like the temperature of the dielectric and the magnitude of the field. In general, the alignment increases with decreasing temperature, and the alignment increases with increasing field strength. If the molecules of the dielectric are nonpolar molecules, the electric field produces some charge separation and creates an induced dipole moment. The effect is then the same as if the molecules were polar. So then, the external field can polarize the dielectric, whether the molecules are polar or nonpolar. The charged edges of the dielectric act as a second pair of plates, producing an induced electric field in the direction opposite the original field. So E naught here is the original field created in the capacitor due to the charges on the plates. And remember that creates a positive charge on this side and negative charge on this side, and that induced charge creates a magnetic field in the opposite direction. The total magnetic field in here is then the sum of these two, which is less than the original electric field. So that electric field due to the plates is directed to the right and polarizes the dielectric. The net effect on the dielectric is an induced surface charge that results in an induced electric field. If the dielectric were placed with a conductor, the net field between the plates, of course, would be zero. So how does this change the capacitance? What if I had a capacitor that was only partially filled? Let's say I have a parallel plate capacitor, separation D, initial capacitance C naught in the absence of a dielectric. What is the capacitance when a slab of dielectric material, dielectric constants kappa, and thickness d over 3 is inserted between the plates? Well, we can look at this situation by first looking at a simpler example. Here I have a set of parallel plate capacitors. Now let's imagine I have an extremely thin piece of metal foil in the middle. It's not going to change the capacitance. It's very small. Inside that metal foil, there's no potential difference. It would be exactly the same as if I had two parallel plate capacitors whose thickness was d over 2. There's nothing different between these two problems. So, if I have a partially filled capacitor, the capacitance of each one is going to be epsilon naught A divided by d over 2, which is going to be 2 epsilon naught A over d. The equivalent capacitance then is 1 over C1 plus 1 over C2. I add those up, I get d over epsilon naught A, or the equivalent capacitance is epsilon naught A over d, exactly the same as I had before. So I can model a capacitor that's partially filled with something as two capacitors in series. Our problem then is exactly the same as having these two capacitors. The capacitance C1 is going to be epsilon naught A over d over 3 times kappa, which is 3 kappa epsilon naught A over d. And C2 then, using the same formula, is epsilon naught A over 2/3 d, giving us this answer. And now these capacitors are in series, so in order to find the equivalent capacitance, we have to add these using our series formula. So 1 over C equivalent is 1 over C1 plus 1 over C2. We get a common denominator, we add them up, and then we see that when we add them up, we get d times 1 plus 2 kappa over 3 kappa epsilon naught A. We can pertify this a little bit, and we get 1 plus 2 kappa over 3 kappa times d over epsilon naught A, which is d over epsilon naught A is just 1 over C naught. So we can invert both sides of this equation, and we get that the equivalent capacitance is 3 kappa over 1 plus 2 kappa times C naught. What if we filled it in the other orientation? What if we had kappa filling the left side of the capacitor. Well, if that's the case, we could draw it just like it's two capacitors in parallel. In this case, C1, the areas of the plates are going to divide, not the distance between the plates are going to divide. So C1 is kappa epsilon naught over d times a over 3, and C2 would be just epsilon naught over d times 2/3 a. These are in parallel, so we can just add it up to figure out the equivalent capacitance. We then have the same denominator, we can just add it up, and we get the equivalent capacitance as kappa plus 2 over 3 C naught. Let's consider another problem. So you have a capacitor is constructed from two square plates of sides L and separation D. A material of dielectric constant kappa is inserted a distance x into the capacitor. Assume that D is much smaller than x. Find the equivalent capacitance of the device. Calculate the energy stored in the capacitor, letting delta V be the potential difference. And find the direction and magnitude of the force exerted on the dielectric, assuming a constant potential difference delta V, ignoring friction. Well, first, the capacitance we can get just like we did in the last problem. We figure out the capacitance of each side. If this distance here is x, this distance here is L minus x. So we know that the depth, the other dimension here that we don't see, is L. So for this half of the capacitor, we get epsilon naught A, and A is L times L minus x over D. And for this half of the capacitor, we get epsilon naught x L over D, and we multiply it by kappa because there's the dielectric in it. We can simplify this a little bit. We see that the capacitance then, as a function of x, how far it is in, is epsilon naught over D, and we get an L squared plus Lx times kappa minus 1. Now that we know the capacitance, we can find the potential energy. The potential energy is 1/2 CV squared. So we plug it in, we can get the potential energy as a function of x. It's going to be 1/2 epsilon naught delta V squared over D times the same L squared plus Lx times kappa minus 1. Now, how are we going to find the force? Well, we know that the force is the derivative of the potential energy. So force is minus du dx in the x direction. So we need to take the derivative of this, and there's only one term that has an x, and that x goes away. So the force is epsilon naught delta V squared over 2D times L times kappa minus 1. We still have the negative direction, so that tells us the direction is negative x. So then there's a force trying to push out the dielectric out of the capacitor, and its magnitude is just given here. So, to review what we talked about today, dielectrics. We talked about what they are and what did they do. We talked about electric dipoles and how electric dipoles allow us to create dielectrics and what happens to them while they're inside the capacitor, and we calculated capacitance change when we use dielectrics.